I'm coming back to the components that we discussed earlier in our lesson. Now we're going to look at things we measure about them. So let's jump right into it. So our voltage source, what we measure about it is voltage. A lot of times we measure differences in voltage, potential drops. Okay, so I'm going to put that in parentheses. But voltage is the key term, and its symbol is capital V. Okay, that makes sense. So there's an equation that I'm just going to throw at you. I'm not going to explain to where it comes from, that defines voltage. All right, so voltage is defined as energy or work, but we'll call it energy, per unit charge. Okay, so if I have a 6-volt battery, what that's basically saying is for every coulomb of charge, Q, that moves in the circuit, I will deliver 6 joules of energy. All right, it's just a way of quantifying how much potential there is before we move anything through it. I'm not going to say much more about that, except that based on its definition, the units would be joules per coulomb. And that has a name. You can probably guess. It's a volt, which oddly enough has the same unit as our variable itself. So if I might say V equals 6 volts, V equals 6V. So that's the one measurement where the unit and the variable have the same symbol. So that's why. But you want to understand the joule per coulomb part. Alrighty. The wires and conductors. Alright, so what are they there for? Well, they provide charge and the charges move through them. So one of the key things we want to measure about that charge movement is their flow. So we call the charge flow current, electrical current, and its symbol is capital I. Not sure why. C is already taken for, well, it's not really taken for anything. Current is widely misunderstood at what it means. Its definition, in terms of an equation, is the rate at which charge moves through a circuit, Q over T. This is not to be confused with the speed at which the charges move. That's always a distance divided by time. Q over T basically is like mass flow rate. Think of when we were doing water moving and we had mass moving. It's how much mass passes by a certain spot in a river. We'd have a lot of mass moving by for a wide river versus a narrow river, irrespective of how fast you're moving. So in a circuit, if we were to zoom in on one part of the circuit, we were to measure the amount of charge that moves by in a unit of time, that is electric current. Okay, so the charges could be moving really, really slowly, which they actually are, but if you have a whole lot of them moving by a given spot, then you have a large electric current. And so on this definition, we see that Q over T, it's going to be units of coulombs per second. And a coulomb per second has a special name called an ampere, or an amp for short, and that's given a symbol, letter A. Okay, so let's talk about that a little bit more conceptually. So current is by definition the flow rate of charge. In other words, if mass flow rate was m dot, current would be q dot, or just Q over T. All right, and all the necessary charges are there. That's the sea of mobile electrons. All right, why do we care about current? Because current is, if it's a moving of charges, why do we want charge moving? Because they're delivering something, they're carrying something, they're carrying energy. And so if you've got more current, you're going to deliver energy at a greater rate to the load. So more current leads to more power output or energy output. Okay, so it should be pretty straightforward. If I think of charges like little trucks carrying energy from one place to another, the more trucks that I have moving by, the more power I can deliver. The question is, how do you get more current? Well, we'll address that at another time. Our body, especially our skin and muscles, are very sensitive to current because our muscles and the nerves work through electrical currents. So if you're wondering how big is an ampere of current, well, ampere of current, if we were flowing through something, is 1 coulomb per second. So that should kind of give you an idea that that's pretty large, because a coulomb is a huge amount of charge. So if we were to have as little as 1,000th of an amp flowing through us, that can be painful. You would not like that feeling. Okay? If you up it to 15 thousandths, then you lose muscle control. All right, so that happened to me last year, where I grabbed a hold of 2 wires and I had a few hundredths or a few thousandths of a current, amperes of current flowing. I could not let go of them until I fell back, and that's very, very, very painful. If you only go up to 7 hundredths of an amp, that's enough to stop your heart. And that's what the danger is with electrical circuits, at least in the home. The ones we'll be doing with the class, they're not going to be dangerous. And if you get 5 to 10 amps, well, that's going to fry your muscles, okay? Now you're bypassing all your nerves and all that. You're just going to cook your muscles, and that's really what an electric chair does. So if you want to deliver a lot of energy, you want a lot of amperage, okay? That's what hurts. That's what kills. Voltage doesn't kill or hurt. It is amperage does, but usually high voltage leads to high current. And that's actually what I talk about here. The amount of current depends on 2 factors, okay? The primary thing is the voltage across the circuit. And another one is the resistance of the load. And we'll discuss that later on next week, okay? So just understand, you can't just dial in a current and whatever current you want. It's a response to how you set up the circuit. And one thing you control, 2 things you control in a circuit are what you put in the circuit and the voltage. All right, so the last measurement that we want to look at is power, okay? The rate at which energy is developed in the circuit, usually in the load, right? The whole point of setting up a voltage source and having current flow is to deliver energy. So the load resistor, one of the things we can measure, this is another thing, but we'll come back to later, is power. Of course, that's P. We already know that P is by definition energy per unit time, the rate at which we're converting energy. And of course, the unit is a joule per second, which we already know is a watt. So what we want to do is we want to be able to relate voltage and current to power, because if you want power delivered, you need current flowing and you need an energy input. So there should be a pretty simple connection between the two. Okay, in fact, we can use in units. So I'm going to come back here. So more power requires more voltage and or more current. All right, so how can we get power from these? Well, let's look at the units. The units of power are joules per second. We know that voltage has units of joules per coulomb, and we know that current has units of coulombs per second. So I don't think it takes too much to figure out that if I have some combination of these 2 measurements that give me joules per second, what would I have to do mathematically? Well, if I multiply them, I see that the coulombs cancel out, leaving with joules per second. So what that tells us then, whoops, I'm going to come back here. I guess that's the definition. Let me add another thing here. So power, power by definition is energy per unit time. And then in an electrical circuit, it's most easily calculated as the product of voltage times current. Okay, so we'll be using that quite a bit. So we have 3 new equations, voltage, current, and power. They should be in your reference tables, so you don't have to memorize them. So, all right, so let's do an example putting some of these equations into use. I'm going to do only a few of these because I skipped over how to do the cost of electricity. We'll come back and do that in class. So a pretty straightforward problem. Example 1. I got a hairdryer. We plug it into a standard US outlet, and that's important, and it draws 12.5 amps of current. So that's a lot of current. So it tells us it's probably a pretty powerful device. So we can ask, what is the power output? Well, if you go back to the table on the other side, and we define power, the general definition is power is the rate at which you do work. Well, when you have electrical measurements of that, we can do a shortcut and say that's just nothing more than the voltage across the circuit multiplied by the current that is drawn through the hairdryer in this case. Well, we're given the I is 12.5 amps. Well, where is the voltage? Well, that's where the standard US outlet comes into play. So that's something you want to remember, is that voltage is 120 volts. So now we can easily plug it in, 120 volts times 12.5 amperes. Pretty straightforward. Gives us 1500 volts times amps. You could put that, and that would be okay, but I'm going to go with the standard watts. All right, so there's a lot of different ways you can express power. It's a voltage, volt amp, a watt, a joule per second, etc. Okay, next question. How much energy is transferred to the toaster after 15 minutes? So this is what we're going to have to pay for. And we'll do the calculation for paying later, but we can do the energy right now. It's pretty straightforward. So energy in our equations is W. Okay, so I can use this relationship up here because I know the rate at which the energy is being produced. We just figured that out, the power, multiply it by the time. But we got to be careful about the time because it's given in minutes, so you got to make the conversion to seconds. Sometimes we'll have to do it to hours for reasons we'll see again tomorrow. So 15 minutes to get it to seconds multiplied by 60. I think you guys can handle that. That's 900 seconds. So we do 1500 watts multiplied by 900 seconds. We're going to get a big number, and it's 1.125 times 10 to the 6th. Okay, so it's 1.1 million. What units are we going to put here? Again, you have a lot of options. You know it's energy, so it can be joules. You're taking watts and you're multiplying it by seconds. You can leave it as a watt second. That is legit. That's the same as a joule. You want to know that. Okay, so I'm going to leave it there. We got 1 million watt seconds. So that sounds like a tremendous amount of energy, but a joule is really not a whole lot of energy. Okay, I'm going to skip C, I'm going to skip D, and I'm going to go down to E. How many coulombs of charge moved across the heating coils at this time? Okay, so what do I mean by that? Well, we have a circuit, and in that circuit, we've got charges circulating around, delivering energy from the voltage source to the hairdryer. So one question we can ask is, well, how much charge that is? So what's the symbol for charge? Hopefully you've forgotten. We're going to call that Q. You can use the uppercase or lowercase q here. It doesn't matter. And what do I know about the situations? Well, I have the original information, so I'm going to write it right here. In this time, so that means that's the 900 seconds. What else do I know about this hairdryer? Well, we found out that the power was 1500 watts. We know that the voltage across it is 120 volts. We know the current through it was 12.5 amps. And we know the amount of energy used, which I'm not going to write down because I already know it's not relevant here. So how would I relate charge to any of these? And this is where you might have to do a little bit of digging. So if I go to the other, if you turn your paper over to the chart, where do you find charge anywhere in there? You see it in a few places. Okay, but the one that's most straightforward that relates it to time is the definition of current. Current, by definition, is the rate at which charge moves, not how fast it moves, but the rate. So I can rearrange that and say the amount of charge that went through there is equal to the current multiplied by the time. Now I have those numbers. So let's see, current is 12.5 amps multiplied by 900 seconds. And if I do that on my trusty calculator, I get, holy moly, 11,250. What units? Well, I could put an amp second. That's okay. But we should also expect it to be coulombs. And whoa, wait a second. That's 11,000 lightning bolts worth of charge moved through that hairdryer in only 15 minutes? That sounds pretty dangerous. So we can ask, where did all that charge come from? Well, remember, the key thing about circuits is we're not building up all this extra charge. We don't have an excess of 11,000 lightning bolts there. It's already there, okay? It's already in the wires or in the circuit. It's not just in the wires. It's everywhere in the circuit. That's part of that circuit. It's not extra charge. Remember that the circuit is always neutral, so we don't have to worry about getting shocked from those charges there because they're no different than the charges in a regular piece of wire. You touch a regular piece of wire, you don't get shocked by all those charges in there. So when we just move them around to get the energy that we calculated prior, we're going to need to move that amount of charge. Remember, in a wire, there's essentially unlimited amount of charge. That's the great thing about current electricity as opposed to static electricity. I don't need to build up all that extra charge to get energy out of it. Okay, so that concludes our examples. We'll come back and do C and D in class. Please come in with any questions.